Well, as I said, this is a continuation of what we presented at the last conference. These experiments produce excess heat with a nickel mesh with palladium burnished on it by rubbing, and I mean physically rubbing like this with your hand, up and down, back and forth, turn it over, do the other side. It's a very crude method. Heat is measured with an airflow calorimeter. It's a great big plastic box with two reactors placed side by side. One is active, the other is the control. Halfway through, you can swap them if you want. It's shown here without the insulation, so you can see inside, and there's two gigantic reactors in it. This is what it looks like during the test with bubble insulation on the inside there. The air goes in the bottom, it gets warmed up from the reactor, and it comes out warmer. That's all there is to it. You measure the input power, the air temperature change, and the air flow rate. And here's one of the better results from the previous conference. This is 100 watts of heating in, 112 watts power out, 12 watts excess. Unfortunately, with this calorimeter, that's close to the margin because it can only measure out 2 watts with any kind of confidence. And here is the best result from this year. 50 watts in, 300 watts output, 250 watts excess. This is with the R20 reactor. That is the 20th reactor that Mizuno has constructed. And this result is far above any possible error, in my opinion. As I said, this is an airflow calorimeter. The gray line represents the heat measured with the air temperature difference alone. No adjustments at all, just, anyway. The orange line is the total after adjusting for heat lost through the chamber walls through that insulation. At these temperatures, at the temperatures of this particular test, losses are about 20%. That's a very high-powered experiment. Most of them are lower power. Losses are much lower, usually. This graph is even more compelling, I think. This is the raw data, the outlet minus inlet temperatures from the excess heat run, the blue line on the top there, and the orange line is a 50-watt calibration with the same very recently, just before this test. The blue line is, as you see, it's 11 degrees warmer than the calibration. That's a huge temperature difference. It's measured with RTDs, with mercury thermometers, with thermocouples. It's measured many different ways, and they all agree. There's an 11-degree difference. Okay, this is a typical result with the previous reactor, the R19. This is not as spectacular as the R20, but it's definitely positive, in my opinion. Again, the gray line is the heat measured from the air temperature difference alone. The orange line includes the heat losses from the calorimeter walls. And the total is about 109 watts, 108 watts. The perturbation here at about 4 hours is caused by a visitor that day who brought his own instruments, and he's moving things around and putting his thermocouples and so on into the device there. And he's putting his own anemometer in the flow. So he confirmed the four parameters, the input power, the inlet and outlet temperatures, and the air flow rate. His instruments were smack on exactly the same for the inlet power and temperatures as you would expect, very close on the airflow. It was a little bit higher, about 16% higher, because it's a different kind of anemometer. Anyway, this is a confirmation. It's a reality check. And it shows that there's no gigantic error in the calorimetry. And it would have to be a gigantic error for this to be wrong. This is not a replication, but I consider it the next best thing. And by the way, several other visitors have been there, and they have all confirmed the measurements, including me. And Mizuno himself has redundant instruments. He has 3 power meters and, as I said, numerous thermometers and thermocouples. So, okay, so at first glance, this is not as impressive as the R20 with the 11-degree temperature difference. It's only 5 degrees difference. If you convert the input power to the calibrated temperature, the difference is about 5 degrees instead of... the reason why it's so much higher input power is because it's externally heated. So it takes 216 watts to reach the operating temperature instead of only about 50 watts. But as I said, if you convert it to temperatures, it's a 5-degree temperature difference. I think that's as convincing as 11 degrees myself. Okay, well, that's a noisy calorimeter. It's unfortunate. It's reliable. It's reasonably accurate, but it's imprecise because the ambient temperature is constantly fluctuating. That's the yellow line there, and that's picked up by the output, the gray line. It doesn't. That's a calibration there. It shouldn't be moving at all, hardly, but it is because of the air temperature changes. Well, okay. I'm not going to be convinced by this until there are several replications. I'm holding out for 4 or 5 good replications, independent. And several replications are now underway. People are making good progress. But most of them have only just begun, and some of them have found, for example, there's no palladium on the nickel mesh at all. They rub it, and nothing happens. It just, the nickel wears off instead of getting palladium on it. One person reported preliminary success, Zhang, H. Zhang, and he sent me the results right here. He's got a much better calorimeter. It's a Seebeck calorimeter. His meshes did not produce heat for about a week or two, and he kept gassing and degassing, which is what we recommend. And then they began to produce 4 watts and then 9 watts. And then finally, the first 3 positive runs produced about 111 kilojoules. The difference is it goes up, as you see, and then after about 3 hours, it gradually fades away. And then it continues at about 1.8 watts here. But that's quite different from what Mizuno has seen. And Mizuno suspects this might be some sort of chemical effect. It seems to me that 111 kilojoules is too much for a chemical effect, but that's what he said. Okay, well, we published a detailed recipe describing how to do this in as much detail as we know. And it's been downloaded 6,800 times. This part that I've put on the screen here describes how you clean the mesh. It says you're supposed to wear gloves, you're supposed to wash in detergent, water-resistant sandpaper, and so on and so forth. It includes many details that I do not think you really need to know, such as the brand of the detergent. But I thought, it might make a difference. You don't know, so I included both the brand name and from the website of the manufacturer, the ingredients there. Yeah, it's a very cute name too. That's why I put it on there. It's cute though, which means squeak, squeak, squeak. Some of the people trying to replicate have taken SEM photos and they have found interesting things, such as materials left on the mesh after washing with tap water. So they asked me, what does the tap water in Sapporo have in it? So I looked it up and I put a very detailed listing of what is in there. There was various other questions and Q&As and so on. So we published a supplement to the original paper, and we keep adding stuff to it as people ask questions. So if there's something else that you want to know, just ask me and I will add it to the supplement. And we've done some other things to assist people replicating. We distributed some as-received meshes from the vendor, and Mizuno is now burnishing some meshes himself, rubbing them with palladium and distributing them. But nobody's had a chance to use one yet. That happened last month. And here's the best thing we're doing. The most promising step to assist people, I think, is he opened up the reactor with the R20 reactor and removed the mesh that produced 250 watts excess, and he's going to send it to some very good laboratories with advanced diagnostics to have a look at it. And that's already underway. He may have mailed one this week or next week. And for us, the best news is they're going to do all of that for free, so we don't have to pay for it. That's great. And if you think of something else that we might do to assist in replication or any questions, please ask me. Now, when people go about doing this, I urge anyone to follow the recipe as closely as you can. Please don't imagine that I'm standing here saying we're the experts and we know what is best and you should shut up and do as you're told. I mean just the opposite. I mean we don't know what makes it work. We don't know what we're doing here. This is more art than science. So if you can't make it work, we have no idea why not. We really don't have many suggestions. But I think the detailed analysis of the used mesh will tell us a great deal more. And by the way, when I say people, I hope that people can replicate, I mean I hope they get 10 or 12 watts, like the way Mizuno was getting last year. I'm not hoping they get 100 watts. That would be a miracle, not a replication. And by the way, Mizuno himself was not able to get 250 watts in his next set of tests. So let me just go over the calorimetry real quick. It looks like this. It comes in from the Hewlett-Packard gadget into the computer in a spreadsheet, which is actually a lot longer than that. The first columns are collected, the next columns are computed, and it does the calorimetry every 5 seconds. The whole thing over from scratch. It's not as I said, there's 4 main parameters. There's the input power, the inlet and outlet temperatures. They are easy to measure. They've been measured many, many times with external instruments. I'm sure they're right. The only difficulty is the air flow rate, right? When people look at this experiment, the reviewer of the previous paper and several others said, aha, you've forgotten. The flow rate is variable. It's fastest in the middle of the pipe and it's 0 at the edges. And they send me this slide right here, the laminar flow slide. And I say, aha, we know about that. We tested for that. And we know the flow is turbulent with type B and it's well mixed. And we know this because Mizuno did a traverse test, which is to say, we got the blower right there. The air travels down the blower to the round orifice at the end, which is 66 millimeters in diameter. And in a traverse test, you hold the anemometer probe in the center at point 1. You take a reading. Then you move to point 2, and then 3, and then 4, which brings you right close to the edge, and then 5, 6, 7. And you find the airspeed is the same at every point, as to the limits of this anemometer, which is 0.1 meters per second. It's uniform, and here's the results that show it's uniform. The first 7 points at, what is that, about 1 watt of input power to the fan, you see all 7 points are right on top of one another. And the second set of points, again, they're all on top of one another. And the third set right up, and then up to 5.5 watts of input power with that fan. We also know the air is well mixed because the Reynolds number can be computed, and it comes out 18,000. Anything over 2,300 is turbulent. Well mixed, well mixed. And finally, we know it's well mixed because you can run the calorimetry backwards. You can compute the air flow rate from the other 3 parameters. With a low power calibration, 10, 30, or 50 watts, there is very little heat lost from the walls. So you assume that all of the heat is captured in the air flow, and then you compute the weight of air is energy divided by temperature times specific heat, and that comes out within 1 or 2% of the measured value from the instruments. And I'm sure those first 3 parameters are correct. I really have no doubt. The other difficulty with the calorimetry is determining how much heat is lost from the walls, and we estimated this by measuring heat recovery at different power levels. With 100 watts, the temperature difference is 5 degrees Celsius, and you multiply the weight of air times specific heat of air, blah, blah, you get up 84 watts recovered. At 200 watts, 179 watts are recovered, and so on and so forth. And we graphed that by input power and also by the temperature of the reactor surface. And from that, you can derive a function to estimate losses at any power level. And the black line on the right shows that it works pretty well. This calorimetry is not precision. It's not high precision. It's only good to within a few watts. So. By the way, we don't need to make that adjustment. We can ignore the losses from the cell wall, as I showed earlier. The heat calculated from the airflow temperatures alone greatly exceed input in almost all of the tests in the last year or so. So this is just icing on the cake. You can ignore those losses if you want. So the question arose, why did the R20 reactor work so well compared to the previous ones? And Mizuno thinks the big improvement is the cell geometry. He thinks Well, he moved the heater from the outside of the cell, that spiral thing on the top there, to the inside, smack in the middle. And that seemed to improve performance. And it's a good question why, but we don't really know. However, the biggest contributing factor by far is the mesh itself. Materials are the key to cold fusion, and we do not understand the mesh well enough to predict performance. They vary tremendously from one mesh to the next. Last month, in August, he made a new mesh and a new reactor with the same geometry, the same R20 geometry. And the excess heat is only, unfortunately, it's only about 20 or 30 watts as of now, which is much less than the 250 watts he saw earlier this year. Okay, well, do not despair. This is not the end of this experiment. It's likely to improve with exercise. That is, gassing and degassing repeatedly will probably increase the output. And a few years ago, most of the meshes did not produce any heat at all, zero. So 12 watts was an excellent result a few years ago. So we're thrilled to see 30 watts. And I think the new geometry is probably the reason why it's working better. And this is sort of interesting. You can see there's a periodicity at the beginning of the sample as it's run here. There's cycles lasting 1.5 to 3 hours each. The sample is spontaneously heating up and cooling down, and it's also loading and deloading. And the heat production is linked to that. This is not under Mizuno's control. He's not making it happen. It just happens by itself, as I said. And there's something, it's an important hint about the nature of the reaction. Obviously, it shows the importance of flux. But it's not clear whether the flux is causing the heat or the heat is causing the flux. But when you deliberately induce flux over and over again, that definitely improves the reaction. And here's this is a closer look at the pressure and D2 concentration waves that are causing that thing. Well, here's the biggest problem with this experiment, which the skeptics have totally overlooked. It's too stable. It's very stable. It's far too stable, in my opinion. It makes me very nervous because I get a feeling that this might be some sort of instrument artifact. It looks like it's producing a fixed percent of input power. It's ironic that the fluctuations from the most recent result give me more confidence that the effect is real, because I can't imagine an instrument artifact that would cause like periodic fluctuations an hour and a half, 2 hours, 3 hours, on a random time scale. That doesn't happen. It's even harder to imagine that it would correlate with the loading and the deloading, which is measured with the gas pressure. The pressure gauge is not affected by temperature. I'm sure about that. So the temperature fluctuations and the pressure are independently measured, yet they are correlated, which I think rules out an artifact. So here's a bonus slide from Ed Storms, who has taken a great interest in this experiment. He wrote a short paper, which is uploaded to leonardcantor.org, titled "The Relationship Between the Burnishing Process Used by Mizuno and the Storms Theory of NAE Formation." That's the nuclear active environment. And he provided this summary, which I'm going to read with some comments, some kibitzing by me. He said, "The Storms has made an effort to identify the important variables involved in the Mizuno method, which is critical to successful replication." That is to say, what he thinks is critical. These are: 1, the amount of sanding changes the amount of surface on which the PD is applied, with increasing sanding expected to cause increased excess power. However, too much sanding will weaken the wires so they will bend rather than acquire palladium. And that's exactly what the people who are trying to replicate have told me. Too much sanding and the wires just bend or break right off. And they find no palladium at all in some cases. 2, the amount of D reacted with the metals will determine the amount of NAE that can be produced. However, the NAE is only produced during a deloading event. Ed thinks that. Therefore, for success to be achieved, deuterium must be first acquired by the metals, and then the D has to be removed, as explained in the paper. And Mizuno's observations support this, and so do Zhang's. It didn't work at all until they went through several cycles. And finally, he said, 3, the effective temperature is critical, with the activation energy calculated from an Arrhenius plot, which Ed has shown in his paper there, being an important diagnostic for the Lehner process. The Lehner process is expected to show a logarithmic increase in excess power with temperature, and what do you know? That's exactly what Mizuno found. And by the way, that is one sample run at different power levels. Each point is 1 day, up and down, back and forth. If that was different samples, the points would be scattered all over the place. One sample shows that pattern, but any one sample does. So finally, he concludes that a runaway is possible at a critical high temperature. And that's what Ed says, and I hope he is wrong. But we'll see. And finally, there's this cute photo that Mizuno sent me last winter of the R20 being used as a room heater. This is the world's first cold fusion space heater. He took the picture without the power supply and without the deuterium gas tank. This has inside it the mesh that produced 250 watts in the calorimeter, with 50 watts of input in the temperature that produced. When he raised the temperature, it began producing much more than the calorimeter can measure. So he took it out, and he put it in that reflective heater, and he used it to heat a room instead. And he put about 300 watts of input power, and it produced as much heat as a ordinary room heater, which is about 2 or 3 kilowatts. Space heaters like that are very common in Sapporo, so you sort of know how much heat they're producing. So this is a very rough approximation, but we know that it was producing it somewhere around 2 or 3 kilowatts. And if it was only 300, the input was 300 watts. That's what you get from 3 people standing around in the room. That doesn't make the room any hotter at all. So that's it. That's what I have to say. Thank you very much. Here's the references.
Okay, we'll start with questions and answers. We have 8 or 9 minutes, so we have plenty of time.
Oh, by the way, speaking of Q&A, if you have questions that I don't know about, the best thing to do is to write them in English, translate them into Japanese, and email them to Mizuno.
I actually have several questions for you. What was your loading? Or can you anticipate it or estimate it?
It's actually, no. Mizuno measured it by measuring the gas and gas pressure. He kept a very close inventory of that. And that's in the paper. It's described in some detail.
Do you know what the number was?
No, I don't recall anything without the
What
paper.
was the size of your nickel mesh? And I mean both mass and the dimensions.
Yeah, I wish I had the paper at hand. The paper is already on the internet, and it's all there. And 50 grams of palladium is added to it, but palladium is probably not the active thing. It's probably the nickel.
Right, but you don't know how many grams?
I know exactly, but it's in the paper, which is right down there.
Okay, all right, right down there.
No, it's a 20 by 30 mesh, which doesn't weigh very much, and there's 3 of them. And you put them on top of one another, you roll them up, you put them into the cylinder.
Oh, you're rolling them up.
And then they unroll, and they stick up against the walls.
Okay.
That's very important.
And did you have lithium electrolyte in the reactor?
No, there's no electrolyte at all. No electrolyte.
Were you measuring the child products?
That's why we're sending it off to the super good lab, because he doesn't have the equipment to do it. Actually, Mizuno has a lot of equipment, but it was damaged in an earthquake last year, and he hasn't been able to repair it for the most part.
All right.
So
And my last question is, how much current was going into the sample?
the current is going into the heater. It's the Joule heater. There's no current going in the sample at all.
Oh, you had no current?
In the previous experiments, the nickel was an anode in glow discharge.
Okay.
So there was current going into it, but
But
in
not in
this
this
set of
one.
experiments, it's just gassing, repeated gassing, loading and deloading, and heating up and cooling down.
Okay, thank you.
Hello, here. Do you have some pictures of the R21 reactor?
Of the what? I'm sorry.
Do you have some pictures of the R21 reactor?
Yeah, I've got lots of pictures
I don't see
on
it.
the paper, but not so many here, is there? No, I don't have. This is the.
Yeah,
Oh, the
yes,
R20.
the
That's the
R20,
R20
it's
right
the
there.
R20, yes,
There's the R19 shown back
The
there.
21.
That's got external heating. That's really the only big difference between them.
But you don't have the pictures of the R21. You are talking just the slide after.
The next one,
Yeah,
one.
you are talking about R21, but there are no pictures.
I don't know what you're saying. The R21, no, I don't have a picture of that. It just got made. The geometry is exactly the same as this one. Why he keeps making different reactors, I don't know, honestly. But he's got 20 of them sitting there in the lab. Yeah. Yeah. Well, they've been getting smaller, by the way. The first picture I showed was a 50-kilogram reactor. This one's around 10. They're getting smaller and smaller and simpler, which is a good thing. So somehow he believes that putting the sheath heater in the middle made a huge difference. It reduces the input power to reach the critical temperature, so that's obvious. But beyond that, it also seemed to improve performance. Perhaps there's some, I don't know.
Chad,
Yeah.
is the current into the heater AC or DC, and does it produce enough magnetic field to have an effect on the mesh?
That's a very interesting question, which he has been cagey about answering, to be honest with you. Just these experiments just began 3 or 4 months ago, and I don't think he's worked that out yet. So as soon as he does, we will put it in the supplement. I think it's at Variac. It was when I was there.
Sorry, I have a couple very simple questions. How many R20 reactors have been in the service so far?
Oh, the R20 is one reactor. R21 is another one. So that's 2 of these. The new geometry, he's made 2 of them. He made 19 of the previous ones, which are externally heated, including gigantic 50-kilogram ones for glow discharge.
The question is about repeatability or reproducibility of this result.
The reproducibility is a function of the mesh. But this one seems to, when you take the same mesh and put it in an old reactor and move into this one, it works better, presumably because of the geometry. But if the mesh is going to work, it will work with any reactor. I think the mesh is probably better than it used to be because he's been much more careful in his recipe to make it, to clean it off beforehand and to rub it repeatedly. He rubs it until it gains about 50 milligrams in weight. And other people who've been trying to replicate this have been rubbing and rubbing and rubbing, and it's gotten lighter. There's no palladium at all. The nickel is going off in little pieces into the dish there, and they look at it in a scanning electron microscope and they see nothing. So apparently rubbing is an issue, and that may be because of the palladium. And the details of the palladium we're going to send it to this laboratory, and they will tell us what's in it.
Okay, and one more question is, what is the maximum duration of the excess heat generation reaction for this R20 reactor?
So far,
with which COP range?
It was 111 days. It was still going, and
111.
It was still going after that, but he turned it off. And then several months later, in the slide I showed, the visitor came to the laboratory. He turned it on again, and it produced almost as much heat as previously.
And what was the range of COP from minimum?
That's what that last slide showed there. What does it show? I can't see it, but well, it's all in the paper. The paper, by the way, is on the internet. You can read it. We published the paper, last year's paper, this year's paper, and a supplement with questions like yours answered. And those data points are about 1 day each over 111 days, repeatedly lowered from very little power to medium power to high power.
And do you think it's possible that the R20 reactor is validated by any third party or experienced LENR scientist? Is it possible to validate by third party the performance of this R20 reactor?
You mean to have someone else test it, that
Yes,
very same
yes.
reactor? Well, now that he's finished with it, maybe. But the most difficult thing, the mesh is the real thing, and we've sent out, as I said, he's making new meshes, but he's not testing them. He's just making them and sending them out. So that maybe they will not work. But he has 3 sheets from the 250-watt reactor mesh. There's always 3 sheets at a time, piled on top of one another, which may be an important factor. He sent one of them to this laboratory in the U.S., and he might send the other 2 to other laboratories if they're interested. And then they can take only a small sample, analyze it, and then put it into a reactor and run it too. Why not? It's being put into a glass vial with air. which I hope does not damage it.
Thank you.
Okay,
Francesco, quickly.
okay, just one. About the long time test, it was necessary to switch on and switch off several times or work it continuously?
The paper shows exactly what it is. Table 1 in the paper, it was run at one power, when I say power level, we should say heat level. The input temperature was raised to a very high level, and then after a while it was lowered, and then put in the middle, and then turned off altogether, back and forth, cycling up and down to produce that curve right there.
Okay.
And every single day, the power level is recorded, and the excess is recorded in Table 1.
Okay, thank you.
Okay, that ends the question and answer.
Good. And as I said, any other questions for Mizuno, ask them to me, we write them out, we translate them, and then we get a straight answer. It's the best way to communicate. Thank you.